Good morning students. Today we discuss the concept that is spectral series. Here as you know very well regarding the spectral lines, in the yesterday's class we discussed about the types of atomic spectra. One is the emission spectra, another one is that is absorption spectra. Here as you know very well, whether either it is an emission spectra or else it is an absorption spectra, whatever it is the spectrum produced by the transition of the electrons taking place within an atom. Here let us consider this is a spectrum. This is a spectrum. Here different wavelengths are there. Here different wavelengths are there. This is the first wavelength, second wavelength means this is first radiation, second radiation, third radiation. This is a screen, means number of the orderly arrangement of the wavelengths that what you are getting on the screen, that is called as a spectrum. In the spectrum here different lines are there. This is a wavelength less, it is having more wavelength compared to first one. This is having more wavelength compared to first and second. Like this arrangement of orderly arrangement of all the wavelengths is there. And here I am calling this first one is a spectral line. This is the first spectral line. This is the second spectral line, and this is the third spectral line, fourth spectral line, fifth spectral line. Here so on number of spectral lines are there up to infinity. Here there is a word, what do you mean by series? Here these are all the spectral lines are there. If you taking one line, you can call it as a spectral line, or if you take the combination of these spectral lines, then you can call it as a spectral series. The group of spectral lines is called as a spectral series. Series is nothing but that is a combination of lines. Getting? By using the atomic spectra, either it is an emission spectrum or else it is an absorption spectrum. Whatever it is the spectrum you are getting, then the group of these lines. What are these lines? These are the spectral lines. The group of these spectral lines are called as a series. Group of lines is called as a series. That's why the definition of this one, the group of spectral lines. The group of spectral lines is called spectral series. Is called spectral series. And here there is an example. Hydrogen atom. I am considering hydrogen atom, and let us consider, in order to study the spectral series, means in order to study what is the wavelength of these spectral lines, there is a scientist called as Balmer. His name is Balmer, and he is a physicist. His intention is to study, to calculate the wavelength of each and every spectral lines. Or you can call it as, he is the scientist. What he did, he found out one theoretical formula. By using that theoretical formula, it is possible to find out the wavelength of each and every spectral line. Getting? He is given that formula, or generally we can call it as, he given the formula in order to find out the wavelength of these spectral lines, or instead of lines in the sense, you can use the word is also spectral series. What he has given the formula, there is a general formula is there. Before going to discuss about that formula, and this Balmer, he taken the example as hydrogen spectrum. He produces the spectrum. That spectrum is called as a hydrogen spectrum. What is the reason? Because he used the atom as a hydrogen. That's why the resulting spectrum we are going to call it as a hydrogen spectrum. And the spectral lines produced by hydrogen atom, he is taking that one, and whatever it is the spectrum, or his intention is to find out the wavelength of those hydrogen spectrum in which what are the spectral lines are there, those lines of wavelength he want to find out. And let us consider he used which atom, that is hydrogen atom. This is the hydrogen atom, and let us consider these are number of energy levels are there. This energy level is equal to 1, this energy level is equal to 2, this is third energy states are there. Let us consider this is lower energy level, compared to this one it is higher, compared to this one these two it is higher, compared to these three this is higher, compared to these four this is higher, so on up to infinity is there. And what he is doing, he is producing the hydrogen spectrum. Means let us consider here number of electrons are there. This is the electron, electron is there, electron is there, here electron is there, here electron is there. Whenever the electron is jumping from higher energy level to lower energy level and it emits the radiation, and the resulting spectrum is called as an emission spectra. Or whenever the electron is jumping from lower energy level to higher energy level, it absorbs the radiation or it absorbs the energy from the radiation. That resulting spectrum is called as absorption spectrum. And here we taken the example as hydrogen atom here. In order to find out the wavelength of each and every spectral lines produced by hydrogen atom, and what is the is given the formula. Let us consider there is a spectrum, there is a hydrogen spectrum is there. That hydrogen spectrum is looking like this, and what he is doing, by using this atom he produced the spectrum. That spectrum, what he is doing in this spectrum, from third orbit to second orbit there is a jumping of electron is taking place. From third orbit to second orbit there is a jumping of electron is taking place. Third orbit is a higher energy level compared to second energy level. When there is a jumping of electron is taking place from higher energy level to lower energy level, it emits the radiation in the form of electromagnetic radiation, and this electromagnetic radiation is getting here. And this one, this is a spectral line getting produced in the screen whenever the electron is jumping from third to second. And next, whenever the electron is jumping from fourth orbit to second orbit, it emits the radiation. Is taken that radiation on the screen, that is this one. This is second spectral line. And next, whenever the electron is jumping from fifth energy state to second energy state, it emits the radiation. Getting that radiation is taking that spectral line on the screen. And again, similarly, from sixth orbit to electron is jumping from second orbit. Again, it emits the radiation in the form of electromagnetic radiation is taking on the screen. And the color of this line is taking it as a red, and the color of this line is that is blue and green mix, and the color of this line is that is exact blue is there, and the color of this line is that is violet. So many number of lines are there, but he considered only 4 lines. What are those 4 lines? Whenever the electron jumping from third to first, one spectral line he got. Electron jumping from fourth to second, that is the spectral line. Whenever jumping from fifth to second, that is the spectral line. Whenever jumping from sixth to second energy state, and is taking that one. And many 7 to second, 8 to second, 9 to second, 10 to second up to infinity. He taken all the spectral lines, but those spectral lines are not clearly visible here. He considered only 4, from third to second, fourth to second, fifth to second, sixth to second. And here, what is happening here? Why he considered only 4? Because these spectral lines are very clear. Remaining are not clear, that's why he left those spectral lines. And his intention is to find out what is the wavelength of this red one, this blue and green mixed one, and this blue one and violet one. And he found out the wavelength of each and every spectral line, and he named this line as H alpha, this line as H beta, this line as H gamma, and this line as H delta. He named the first one is a red H alpha. He given the name H beta, H gamma, H delta. Respecting the color of these spectral lines is red, blue, green, blue and violet. And he used or he given one formula. What is that formula? That is 1 by lambda is equal to R into this is 1 by 2 square minus 1 divided by n square. This general formula this is given by that is Balmer. For what reason? In order to find out wavelength of these spectral lines produced by each other hydrogen atom. And let us consider what do you mean by here lambda? This is a wavelength of each and every spectral line. What is a? This is constant. This one is constant called as Rydberg constant. What do you mean by Rydberg here? That is the name of the scientist. Get it? This is the constant value is there. This is a Rydberg constant. The name of the scientist that is Rydberg. Get it? And next one, Johannes Rydberg his name is, and he given the value that is R value. That value is equal to 1.097 into 10 to the power of 7 per meter. This is R value. This value is called as a constant for every spectral line or every radiation. This is given by the one of the scientists who is none other than Johannes Rydberg. In order to find out the wavelength of each spectral line, given the R value that is constant. By using this formula, we can find out the wavelength of each and every spectral line. And Balmer found out the value that is first what he did here. First one he taken that is for H alpha means red by using this formula. Actually this is what is whenever the electron is jumping from third orbit to first second orbit, take n1 is equal to 2, n2 is equal to 3. And next whenever the and find out the value of lambda. And next whenever the electron is jumping from fourth orbit to second orbit, then take this as a 4 and this as a 2. Whenever the electron is jumping from fifth orbit to second orbit, take it as a fifth and take it as a 2. And whenever the electron is jumping from sixth orbit to second orbit, take this n value as a 6 and here take it as 2. Whenever the electron is jumping from infinity to second orbit, take here n as a infinity and 2 as it is. This is an indicating number of higher orbits. This is ground state for getting this one hydrogen atom here. And he found out the value. And what he is getting? Whenever the electron is jumping from third orbit to second orbit, take this as a 3, this as a 2. Calculate lambda value. He found to be its value is equal to 500 and that is 653.2 nanometer, 3 nanometer. Whenever the electron is jumping from third orbit to second orbit, it releases the energy. You are getting the line on the screen. And by using this formula, he found out the wavelength. He got this much. And this is exactly the wavelength of red one. Not exactly, approximately. This is the red light wavelength. And next, what he did here? Whenever the electron is jumping from fourth energy level to second energy level, substitute 4 here, substitute 2 here, calculate lambda value. He is getting the answer of this spectral line, that is 486.1 nanometer. Next, what he is doing? Whenever the electron is jumping from fifth energy level to second energy level, substitute value here too and calculate lambda value. He is getting the wavelength of this blue light is that is 434.1 nanometer. And whenever the electron is jumping from sixth energy level to second energy level, substitute here 6. This is second as it is. Calculate the lambda found out the energy value, means wavelength value is getting around, that is 464 nanometer, and only he considered 4 by the hydrogen atom. Whenever the spectrum is produced by hydrogen atom on the screen, he considered only 4 spectral lines because these are very clear one, and in order to find out the intensity of these spectral lines, he given the formula, that is 1 by lambda is equal to r into 1 by 2 square minus 1 by this is n square. N is jumping from third to second, take 3, fourth to second, take 4, fifth to second, take 5, infinity to second, take infinity, and calculate the wavelength value. And here number of lines are there, not only 4, he considered only 4 because of these are very clear, but here number of lines are there, he didn't consider those because they are very they are not seeing very clearly. But in order to find out those lines, again some of the scientists are there or other physicists are there, they discovered the wavelength of other lines here. Those are called as, first one is the Lyman series. First one Lyman series is there. Lyman series, he is another scientist. And he given whenever the electron and here whenever the electron is jumping from, let us consider, whenever the electron is jumping from second orbit to first orbit, it emits the radiation, and he is taking on the screen this one. Whenever the electron is jumping from third orbit to first orbit, it emits the radiation, we are taking here. Whenever the electron is taking from next fourth orbit to first orbit, and it emits the radiation, we are taking here. In order to find wavelength of these spectral lines, the formula that is found out by, that is Lyman, the same formula what we use, that is 1 by lambda is equal to r into 1 by n1 square minus 1 by n2 square is there. Here n1 is equal to 1, n2 is equal to 2, 3, 4, so on up to infinity. Whenever the electron is jumping from second orbit to first orbit, it releases the energy. In order to find out the wavelength of that spectral line, use this formula. n1 is 1, n2 is 2. Whenever the electron jumping from third orbit to first orbit, it releases the energy. In order to find out wavelength of that radiation, substitute here 3, here 1, and you are getting lambda value. Whenever the electron jumping from fourth to first orbit, here it releases the energy, substitute 4, substitute 1, find out the value. And this is the formula. And if you point out the wavelength of this line, you can calculate the wavelength of all the lines. That wavelength value should be almost equal to the wavelength of ultraviolet region. For example, let us consider this is gamma radiation, X-ray radiation, and this one is UV light, and next one is visible light is there, and next one infrared, and next one micro radiation, and next one radio wave. Its wavelength is equal to approximately 10 to the power of minus 3 meter is there, and its wavelength is equal to 10 to the power minus 3 meter to 1 nanometer is there, and its wavelength 1 nanometer to 400 nanometer is there, and its wavelength is equal to 400 nanometer to 700 nanometer is there, and its wavelength is equal to 700 nanometer to that is 1 millimeter is there, and its wavelength 1 millimeter to 0.1 meter is there, and its wavelength 0.1 meter to this is 35 kilometer is there. This is the wavelength range of all the electromagnetic radiation. He found out the wavelength of all these spectral lines. The value should be lies between 1 nanometer to 400 nanometer. If add value the wavelength formula is 1 by lambda is equal to r into 1 by n1 square minus 1 by n2 square. Here n1 is equal to 1, take n2 is equal to n1 is equal to 2, take n2 is equal to 3, 4, 5, so on to infinity. Whenever the electron jumping from third to second, take the spectral line. Whenever electron jumping from fourth to second, it releases the energy. On the screen we are getting one spectral line. Whenever the electron jumping from fifth to second emits the radiation, you are getting the spectral lines here. Spectral lines like this, and he calculated the wavelength of all the radiations, and the answer is lies. He calculated the wavelength of all the spectral lines. The answer is lies between 400 nanometer to 700 nanometer. The value of all the spectral lines, that is belongs to in between these two values only. Then what is the conclusion here? Balmer series belongs to which region? Belongs to visible region. And like this, and next third spectral line is found out by the scientist called as Pascal series. Next here n1 is equal to, we are taking this is 3, n2 is equal to 4, 5, 6, so on up to infinity. Whenever the electron jumping from fourth orbit to third orbit, it releases the energy, and you are getting the spectral line. Whenever it is jumping from fifth to third, there is a line. Whenever jumping from electron sixth to third, there is a line. Infinity to 3, so on up to there is a line. He found out the wavelength of all these spectral lines. He is getting the answer that is in between 700 nanometer to 1 millimeter. That's why this Pascal series belongs to infrared radiation. IR means infrared region. And fourth, that is bracket series. This is also name of the scientist. Fourth one is bracket series, and here n1 is equal to 4, n2 is equal to 5, 6, 7, so on up to infinity. Whenever the electron is jumping from fifth orbit to fourth orbit, there is an emission of the radiation, that is the spectral line getting on the screen. 6th to 4, there is a line. 7 to 4, there is a line. Infinity to 4, there is a line. This man is going to find out the wavelength of all these radiations. The answer is lies in between 700 nanometer to 1 millimeter. Then it means bracket series belongs to same. Bracket series also belongs to IR region. Next, last one is P-Pund series. Here n1 is equal to 5, n2 is equal to 6, 7, 8, so on to infinity. Whenever the electron is jumping from 6th orbit to 5th orbit, it releases the energy. You are getting the spectral line on the screen. Whenever jumping from 7 to 5th, it is releases the energy, getting the spectral line on the screen. Whenever it is jumping from 8 to 5, you are getting the spectral line on the screen. And he found out the wavelength of all these spectral lines, and the answer should lie in between 700 nanometer to 1 nanometer. It means that the P-Pund series also belongs to infrared region. This is regarding about the spectral series of all the radiations. This is the spectral series. The first one is a Balmer. He used the example as the hydrogen atom. In hydrogen atom, the emission spectra he produced, he considered only 4 lines, because only 4 lines are clearly observed, named H alpha, H beta, H gamma, H delta, and by using this formula 1 by lambda is equal to r into that formula he used, and he found out the wavelength of all the values and the wavelength of all the radiations. One is the first one is the red, second one is the blue and green, third one is the blue, fourth one is the violet. He found out the answer as like that: 563.3 nanometer, 486.1 nanometer, 434, 410, so on like that. And infinity line, that is he calculated n is equal to infinity 2 as it is. He found out the value of lambda, he got the answer as 464 nanometer. And next he goes to, and for some other lines are there but they are not cleared one, but whenever the electron is jumping from second orbit to first orbit, third orbit to first orbit, fourth orbit to first orbit, but how to find out the wavelength of those spectral lines he didn't give. That's why there is a scientist, he found out that one called as Lyman series. Whenever the electron is jumping from 2 to 1, 3 to 1, 4 to 1, so on up to infinity to 1, then the spectral lines what they are getting on the screen, the wavelength of those spectral lines can be calculated by using same formula, but you have to substitute n1 as 1, n2 as 2. Or if it is jumping from third to 1, n1 as 1, n2 as 3. Or if it is jumping from fourth orbit to first orbit, n1 as 1, n2 as 4. Or if it is jumping from infinity to first orbit, n1 as 1, n2 as infinity. And he found out the wavelength of all the spectral lines, and he got the answer. That answer is belongs to, that is this answer. Answer is in between this and this. That's why this is belongs to UV region. Second, whenever the electron jumping from 3 to 2, fourth to 3 to 2, it emits the radiation. That is the spectral line. Fourth to 2, it emits the radiation. Fifth to 2 emits the radiation. So on is getting the spectral lines. He found out the wavelength of these radiations. This answer belongs to, that is visible region. 400, 700 nanometer he got the answer. That's why it is visible region. So on like that. All the 5 series are there. First 2 are belongs to, first one is a UV region, second one is a visible region, and for third, fourth, fifth belongs to IR region. Ready? Thank you.